Hi, everyone. I'm Jacob. I work on mostly natural language processing at MIT. Today, I'm going to be talking about something a little different, which is the worst possible way to to estimate the parameters of a linear model, and what this can teach us about sort of modern NLP systems and language generation systems. Here we go. OK, so to start off, right, everybody's favorite introductory estimation problem, linear regression. We have some x's, we have some y's. A new x comes along, and we want to be able to predict the corresponding y from this x under whatever the data generating process is. Right, and so as every undergraduate now knows, the way to do this is you take all of your x's and you put them into a matrix. You take all your y's, you put them into a matrix. And then you open up ChatGPT and you paste your x's and your y's into ChatGPT and you ask it to give you a solution to this problem. I wasn't going to do this for real, but I did this when I was putting these slides together, and it produces this very long, very authoritative sounding answer. There's a bunch of sort of intermediate computations and math here. And if you take the actual predictor that it gives you at the end and you drop it back into this problem, it looks a little bit like this. So not necessarily a reliable way to estimate linear regression models right now. And more generally, I guess, this is obviously a kind of ridiculous thing to do. We have already very, very old, very, very good algorithms for solving these kinds of problems. And so it doesn't seem like the sort of thing that we might necessarily need to ask a language model to do, or where it would be an interesting question to ask whether language models, text generation systems, like the kind that we have today, are able to do it at all. Nevertheless, the kinds of things that we can do with these big open-ended text generation systems are becoming, sort of like more and more general. These models themselves are becoming more and more capable, right? So here's an example from what's now, an oldish paper, 2020, showing that these models can do real sort of open-ended text generation. So here's a particular language model, and we'll talk more specifically about what these language models are in a minute, but that is being prompted, right? It's asked to predict what text should come next after this text that we have in light gray up at the top of the slide. So we give it the title of a sort of hypothetical news article. We give it the subtitle of a hypothetical news article. And then we ask it to generate the text of the article itself. And it gives you this long paragraph, right, that are both sort of compatible with the title, describing the sort of thing that you would expect to be in an article with that title, written in the style of a news article, and more or less internally coherent. It's also worth noting that this article is, or the sort of factual content of this article is wrong, that it's describing, as prompted, a sort of real split that happened in the Methodist Church, but the identities of the individual sort of groups that came out of the schism, while plausible sounding, are totally made up. Now, we can do more with these text generation systems than just generate long blocks of text. One of the other surprising capabilities that we've seen as people have started to play around with these things is that they can do instruction following, right? So you can take, again, a sort of generic next word prediction system. You can say, give it as input the text, explain the moon landing to a 6-year-old in a few sentences, and a good enough text predictor will actually respond by following this instruction and by generating some text that specifically explains the moon landing or answers a question, why do birds migrate south for the winter, and so on and so forth. And maybe the last sort of surprising capability that we've seen in these models as they have scaled up and as people have started to play around with them more is a phenomenon that is coming to be referred to as in-context learning. And so what's happening here is that rather than just giving this model the sort of beginning of a document that we want it to complete, and rather than giving it an explicit textual description of the task that we want it to perform, we just give it some examples of that task being performed on other kinds of inputs. So here, we're asking it to do some sort of grammatical error correction task. And we do this by placing, as the input to this model, the string poor English input, I eated the purple berries, good English output, I ate the purple berries, poor English input, thank you for picking me as your designer, I'd appreciate it, good English output. And we fill in all of these pieces like this. So again, all of this text that we're showing in light gray on this slide is text that we as a human user of this system are providing. And notice that the sort of structure of this input, right, is that we have some human-written bad examples, good examples, some human-written inputs and outputs. we've ended here with an input, and what the model is going to generate next is a desired output. And in this case, what we get out of the model is, in fact, a corrected version of the last sentence that we asked for. And so we can specify tasks that we want these language generation systems, these next word prediction systems to perform, again, not sort of in the form of natural language instructions, but in the form of tiny, tiny data sets for these new tasks that we're asking these models to generate. And this turns out, and this was something that was not even necessarily planned out ahead of time, but discovered in these models around 2020, and is something that you can do for a wide variety of tasks. You can do it even for simple arithmetic kinds of things. You can do it for spelling correction. You can do it for translation. You can do it for that grammatical error correction. And we'll see a couple more examples later on in this talk. And I think the important thing to note here is that in some cases, this is more effective, right, than providing a precise natural language description of the task that you want the model to perform, that they actually get better at doing these kinds of things when you give them explicit examples in the input. And just ask them to generate more examples or generate, the output pieces of those examples from that same distribution. And so this, like I said before, this phenomenon is coming to be referred to as in-context learning. And what this is meant to evoke is that there is a kind of learning that looks like machine learning as we're used to thinking of it, or parameter estimation as we're used to thinking of it, but that is happening now not as part of training one of these prediction systems, but actually in the course of figuring out how to generate text or figuring out how to complete one of these documents. And so what this talk is going to be about, the sort of big question that I want to ask today, is basically what on earth is going on here? What is the relationship between this particular phenomenon and learning as we're used to thinking about it in a machine learning setting? And what can we say about the sort of reliability of this process or the limits of this process? I want to note also before I go on here that everything that I'm going to be talking about today was led by my student Ekin Akyürek with a big collaboration from some folks at Google and Stanford as well, Dale Schuurmans and Denny Zhou at Google, and Tengyu who's joint between Google and Stanford. And the sort of broad outline of this talk is to first figure out or discuss just what this in-context learning phenomenon is and what possible hypotheses we might build about what's going on when models are doing this text generation process. And then we're going to ask, with the kinds of models that we have today, algorithmically, what kinds of things might they be able to do? What kinds of things might they not be able to do when presented with these sorts of in-context learning problems? And this is all going to be kind of in-principle arguments just from the structure of language models as they exist today, without looking at any real models. And then we'll actually go out and train some models and try to figure out what's really going on under the hood, and then talk about sort of the implications of this more broadly for research on NLP, research on language modeling. So starting with this first question, what exactly is this in-context learning phenomenon, and how might we be able to describe this behavior? And so to talk about this, right, let's start by being a little bit more precise about what these language models are, what something like ChatGPT or whatever is. And fundamentally, what one of these models is just a next word prediction system, right? Like the thing that sits on your phone as you're writing a text message and tries to generate what word you're going to say next. And so what that means in practice is that we're modeling a distribution over strings, typically natural language strings, but now in practice, kind of anything that you can write in Unicode, and that distribution is represented via just the sort of normal chain rule distribution, one token at a time, with some kind of parametric model that's just trying to predict every word given all of the words that came before. Right, so concretely, right, thinking about what one of these in-context learning examples looks like, we're going to try to model a joint distribution over, for example, input-output pairs with some separator tokens and some input markers and whatever, by just asking what's the probability of the first input, and then the probability of some separator symbol given that first input, and then the probability of the first output, and so on and so forth. Right, and as you might expect, the very beginning of this generation procedure, the sort of first step in this decomposition, is going to be super high entropy. The model doesn't know what it's supposed to be doing at all. If it has actually learned the task that we're asking it to perform, by the end, when we're asking it to predict the x's, it'll know the distribution of x's, and when we're asking it to predict the y's, it'll know sort of precisely the distribution of y's given x's. So how do we actually model this distribution in practice with, sort of in the kinds of language models that we're using today? And pretty much every language model that is in widespread use that you'll encounter, that people are working with in the research community right now, is a neural network, and it's a neural network of a very specific kind called a transformer. There's a lot of low-level details about these transformer models that I'm not going to talk about at all right now, but there are some high-level details that are important for sort of understanding how these models work, and so I want to talk through those things. At a high level, when I'm given an input like this one that contains goat misspelled, arrow, goat spelled correctly, comma, snake misspelled, arrow, what we're going to try to do, and I guess some of the alignments are off here, but hopefully the correspondence is right. The first thing that we're going to do is we're going to take each of these natural language tokens, right? The word goat or the word, or, the symbol arrow or whatever, and we're going to assign them what's called an embedding. We're going to, map each of these words using some fixed dictionary that is itself learned to some high-dimensional parameter vector. And so if you've heard of word embeddings, right, what we're giving this model as input is an embedding of each of these words in sequence. And the first thing that we're going to do, once we've represented each of these words in the input as some high-dimensional vector, is that we're going to perform what's called attention. So every word is going to sort of pick up at every position in this input, we're going to pick up the embedding that we've computed so far, and we're going to take a linear combination of all of the word embeddings that are in the sentence up until this word that we've predicted right now, where the sort of weights in that linear embedding are themselves some learned function of the input. So effectively, when we're looking at this word goat, it's going to decide how strongly, and the reason this is called an attention mechanism, think of it as deciding how strongly it wants to look at all of the other words in the input up until this point, pool them according to sort of how strongly it's looking at each of them, and then build some new representation in context of this word goat that incorporates all of this other information from all of the other words that have come before. And we can do a little extra processing on top of this so we don't lose the identity of the word that we had as input, but at a high level, think of this, the first thing that a transformer does, this attention mechanism, is just taking some weighted combination of all of the other representations that we've built up to this point. And we're going to do this in parallel for every token in the input, right? So we're going to compute a representation of goat in this way, and goat gets to look at all three tokens to the left. We're going to compute a representation of, for example, this last arrow character, and that last arrow character gets to look at the entire sentence that we've seen so far. And so we're going to get, as a result of this entire process, a sequence of now these attention vectors that are derived from our original input embeddings. Once we've done this, we're just going to apply some other learned nonlinear transformation to each of these new vectors that we've built up. This now doesn't look at any other piece of the input at all. It's happening, again, sort of locally in parallel at every step of the input, and works basically the way a normal feed-forward neural network works if you've seen those. But we're doing that now for every word simultaneously. And these two steps together, this attention step followed by this multi-layer perceptron, this sort of generic nonlinear transformation, we're going to refer to as a transformer layer. And we can actually take these transformer layers and we can stack a bunch of them on top of each other in sequence. So we can do this once, and then we can do it a second time, where now when we do that attention step, we're attending not to the original word embeddings, but to all of the, all of the representations that we built at the last step of this procedure. And in practice for big models, you're doing this tens of times or hundreds of times to eventually build up a representation of the entire input sequence that you have. And what we're going to get here at the end, again, is a sort of sequence of the outputs of those final MLP steps, one for every token in this input sentence. And the last thing that we're going to do is we're going to take the very last hidden representation, the last output from the last of these transformer layers, and we're just going to try to decode it into a distribution over possible next tokens using basically something that looks like a log linear model, right? So again, every word in my vocabulary, just like at the embedding layer, is associated with some vector, and we're just going to sort of compute dot products between those vectors and this last hidden representation, and then exponentially normalize to get a distribution over y's. And so what we hope, right, in the context of these kinds of in-context learning problems, is that this distribution that we get over the end places a lot of mass on the correct spelling of snake and not a lot of mass on all of the other words in our vocabulary. Good. So how, having defined this model architecture, do we train them? And in the most basic sense, the training is super easy. You go out and you scrape as much text data as you can get your hands on. You crawl the entire internet. You pay a bunch of people to sit in a room and write sort of nicely structured documents for you. And then you just do maximum likelihood estimation with this model on that gigantic data set. A lot of the challenges here are really engineering challenges more than kind of modeling challenges. And a lot of the reason that sort of OpenAI is able to train these models and people in academia are not has to do with just like the cost of computational resources that you need to really do this at a scale that makes it effective. One thing that I'll say that's not going to be part of this talk at all is that in most modern language models, especially the ones that sort of look and talk like chatbots, there's another step that goes on after this process of sort of learning via something that looks like reinforcement learning from human feedback. That's not really going to be relevant for what we're talking about today. The relationship between that and some of the sort of capabilities that I was talking about at the beginning is still a little unclear, but is part of kind of the modern recipe. OK, so this is the basic transformer architecture. What happens when we actually do this, when we fit this maximum likelihood objective to the entire internet? And what happens is you get a model that is very, very good at a very large number of different things, right? So here are some examples from a recent paper showing good performance on the bar exam, although apparently these bar numbers are actually really sketchy, and this is maybe not something to take seriously. But pretty good performance, if not like top human level performance across a wide variety of things requiring both a little bit of reasoning and quite a lot of knowledge, right? The LSAT, the SAT, the GRE, both the math sections and the verbal sections. And this has been in the news. I assume many people have seen this before. And I think it was surprising is maybe not even a strong enough word, but to many of us in the field, both that just doing this at a large enough scale would get you here, and that we were going to be able to do this kind of as quickly as possible, and that the large enough scale turns out to be only all of the text that humanity has ever written and not something much more than that. OK, good. So among the things that happens when you train a model in this way, like we were talking about before, is this in-context learning phenomenon, right? So here now we can talk a little bit more precisely about what ICL is, or what it would take to be a good in-context learner. And it's something like being able to take a sequence of inputs that looks like this, and have as your output distribution something that places a lot of probability on, in this context, the French word for cheese, and maybe other sort of plausible variations on it. Similarly, if we want to do not machine translation, but sentiment analysis, we want to be able to plug in some examples of sentences associated with sentiment, assign them natural language labels, and be able to predict the appropriate ones. I guess there's some text getting cut off here, but in the right way. And finally, one of the kind of surprising things that happens is that you can do this not just with sort of well-defined problems that you expect to see occurring many times in the training data, like the sentiment analysis problem or the machine translation problem, but with weird made-up problems that surely nobody in the world has ever asked one of these models to solve before. So this thing on the slide, this particular combination of symbols and meanings, is something that Ekin made up the first time he gave a version of this talk, and models, or at least the particular language model that he asked this question to, was able to produce the right output here the first time. So coming back to the original question at the very beginning of the talk, what is it that's actually going on here under the hood in virtue of which these models are able to solve problems like this? And I think the initial reaction from most people in the language processing and machine learning communities was that learning was probably not the right way to describe what was actually going on in these models. And maybe better to think of it as something like task identification. And here's a quote from Reynolds and McDonnell that I think captures this sort of hypothesis about what's going on here pretty nicely. Few-shot prompting is not really learning of skills, but just locating of skills that the model already has. This is most obvious for translation, where you can't learn a new language from 5 examples. And I think the translation case is a clear example of where this is the right way of thinking about these models. In fact, you can't learn French from 5 examples, like skipping ahead. Here, certainly if there's an English word that you've never seen before and you can produce the right French output, some of the knowledge about the relationship between English and French does not reside in the sort of in-context training set here, but has to come from the model's background knowledge. But when we think about these more kind of algebraic puzzle-solving problems, it's a little less clear that this is the right way of thinking about things, right? I think we can be pretty confident that at least then, maybe not now, this particular example didn't appear in the training data for any of these models. Maybe other things with a similar flavor, a similar grammar induction structure, but not exactly this one. And so competing with that hypothesis that we had on the previous slide is another hypothesis that this in-context learning thing is quote unquote real learning, right? That it's capable of sort of taking a training set that fully determines the behavior that you want to get out and using that kind of training set to index within some reasonably large hypothesis class the actual function that you want this model to implement, even if that's a function that it never saw executed anywhere at training time. And so the thing that we set out to do in this project was basically to answer that question, to figure out whether it is possible, even in principle, for something like one of these transformer models to make a version of this hypothesis true, to get them to do real learning, and then to actually figure out what's going on in real models. Yeah, question? That is a great question. I am not sure. We could try it. Yeah. Yeah, I mean, and I think this is, so I'm not going to be able to like produce off of my top of my head the like full exploration that we did here. But no, I mean, that's a good point. And there are also examples of cases where providing this kind of extraneous information actually confuses the model. And I'm sure it's also not the case that you can get 100% accuracy on things in this general class. Other questions before we go on? OK, cool. So yeah, the first question that we're going to ask here then is whether it's possible for these transformer type models to do real learning, whatever that means, even in principle. So to sort of take this hypothesis that we had before and figure out whether there's some class of functions and some class of models for which this is true. And we're going to do this by looking actually at those linear models that we looked at the very beginning of the talk, just because this is a case where we know exactly what the kind of space of algorithmic solutions looks like. It's very easy to generate data, and it's a simple enough problem that you don't have to go out and use something trained on the entire internet. You can actually do all of the learning yourself. One other sort of important caveat to make here is that, in some sense, this question of can a transformer implement function X, where even function X is training some little machine learning model on the inside, was already answered decades ago. We know that neural networks are general purpose function approximators when made sufficiently large and trained on enough data. So really the question here is whether you can do, but the constructions that you use to do that kind of universal approximation are kind of ridiculous. They blow up exponentially in the size of the input and the complexity of the function. So really what we're trying to figure out here is whether you can do this not just at all, but with models that are the kind of size and shape of the ones that we're actually using today and of the size and shape that are showing all those real world results that I was showing you before. Citation is cut off here, but it is to a paper by Garg et al. At Stanford, who around the same time we were doing this, asked a similar set of behavioral questions about just like what kinds of functions extensionally are you able to learn in this framework. Okay, so the way we're going to go about looking at this, right, rather than taking our translation problems from before and asking models to solve translation problems via this word embedding step or whatever, we're just going to generate some input-output pairs. We're going to sample a random weight vector here. I guess I'm showing this as one-dimensional, but these are going to be higher dimensional problems later on. And we're just going to train the model, right, in exactly the same way. And I guess for now, we're not even training models. We're just asking how we can parameterize them to begin with. So can we parameterize some transformer in such a way that we give this 0 as input, it predicts a 0 as output? One thing to note here, we can also, and in the experiments that I'm going to show later on, we are going to train these models both to predict y's given x's and to predict x's given the whole history of interactions that have happened before. Here, we're not going to worry about actually modeling the input distribution at all. We're just going to worry about modeling that conditional distribution. And I think it's actually an open question how much this matters for real training things. Good. So, not to belabor this point too much, we've had linear regression and solutions to linear regression problems since the 1800s. We know that there are lots of algorithms that you might pack into one of these transformers that will solve them. And you can do this by just sort of directly inverting this relevant matrix. You can do this by gradient descent on some kind of least squares objective or something else that looks like that. And so the question is whether we can take any of these algorithms and pack them into one of these models like this. And it turns out that you can do this. The details are sort of mechanical, and I'm just going to give a sort of high-level flavor for one of these. But it turns out that you can show both that if you're sort of trying to fit these linear models via SGD or via batch gradient descent, you can do that. You can do that using a relatively shallow model and using a model that has depth that scales proportionally to the number of steps of SGD that you want to do here, using sort of a reasonable number of these attention mechanisms, a reasonable number of these layers. And second, you can do this not just via SGD, but just sort of by directly constructing that final predictor via a sequence of rank 1 updates to that XTX inverse matrix. Again, there's a lot of sort of low-level mechanical stuff, but just to give a high-level flavor of how this works, we're going to define a little calculus of operations that we can implement inside a transformer for sort of moving data around and applying linear transformations to it. And then once you have these things, you can just chain them together and implement really any algorithm that you choose that bottoms out in these operations. Right. So what are the things that we need to do, for example, paradigmatically to implement gradient descent, or even just the first step of gradient descent on this objective? Well, one thing that we're going to need to be able to do if most of the processing is going to get done by these multi-layer perceptron units, these feed-forward layers that we were talking about before, is just to consolidate our data, right? So we need to get our x's and our y's into the same kind of part of the representation space so that the model can work on them. We're going to call this a move operation, and it turns out that you can implement this move operation pretty simply using that attention mechanism that we saw before that can just sort of pick up a piece of the hidden state from one input and move it to the next time step. So the first thing that we're going to do for SGD here, for example, is just accumulate the x's into our y's. Another thing that you need to do here is take affine transformations, right? For example, on this first step, we have some initial guess at the weight vector. We need to dot that by our initial feature vector to figure out what our error is. And so we need some way of doing affine transformations. And affine transformations are in some sense like the only thing that these multi-layer perceptron units can do. And so this is very, very easy to implement using that MLP layer that we were showing before. And then the last thing, and the thing that turns out to be the sort of fussiest piece of this, is computing dot products between pieces of these feature vectors or between feature vectors across time. You need this, for example, to scale your input by your prediction error when you're doing an SGD step. And it turns out that you can also do this by exploiting a bunch of very low-level details in the way these MLP layers are defined in practice for sort of real-world transformer models. And this is like, I don't know, very inside baseball, probably not worth going into too much details, and if they would make sense, you've already read this paper. But basically, you can get the nonlinearity in that MLP to pretty well approximate element-wise multiplication of a couple of these vectors, or scaling by a scalar, if you get things very close to 0 and do things in the right way. And once you do this, right, once you've sort of defined a transformer chunk that does this move operation, a transformer chunk that does this affine operation, and a transformer chunk that does this dot operation, then all you need to do to show that a transformer can implement SGD is write the program in terms of these operations that actually does so, right? So here, for example, is the one that does SGD. You can write a corresponding one for doing the sort of sequence of rank 1 updates with the Schuurman-Morrison formula. And that's all you need to do to generate these kind of in-principle demonstrations that transformers can do real in-context learning. One other nice kind of detail here is that all of those three things that I was showing before, you can actually consolidate into a big generic kind of like read, transform, and write operation that you can implement in a sort of generic way. And there has been some follow-up work since we put this out, sort of developing just generalized versions of that, like generic transformer read, attend, write operator to make, in some sense, nicer programming languages for describing what goes on, or what kinds of functions you can implement with these transformers, and coming up with tweaks to this architecture. Good, and so maybe unsurprisingly, but it's nice to see that in fact it is possible to parameterize these models so that they implement real algorithms that we've written down ahead of time, and thus it's possible, at least in theory, that these transformers that we're seeing out in the real world, for at least some subset of these in-context learning problems, are doing real ICL. And so, of course, the natural question now is, what is happening in practice? When we actually train these models on the distribution that we assumed we were going to get in the previous part of this talk, do they actually converge to the kinds of solutions that we were expecting to find here? And so we can ask this in a couple of different ways. One is, just do you get the same kinds of generalizations that would be predicted if you were implementing some version of real learning, as we've described it before? And second, what's the relationship between a model's ability to discover the solution and lower level details about the capacity of the model, how big it is, and other implementational things? So we're going to try to answer both of these things, and we're going to do it right by now just taking this basic learning setup that we assumed for constructing some in-context learners before, and actually now just training models on this data, right? So we're going to sample some weight vectors, we're going to sample some input vectors, we're going to generate some y's using the weight vectors and the input vectors that we sampled. And in particular, right, we're going to construct a sequence, or a data set of sequences, where each of these sequences was generated by a single one of these weight vectors, right? So, here I have a bunch of y's that were generated from some particular w, sampling my x's from some normal distribution that's going to stay the same. And I'm going to present the model with this sequence and ask it to make a prediction at every step of this sequence. And then when it gets to the end of the sequence, I'm going to sample a new weight vector, and I'm going to give it a sequence of xy pairs that were generated by that new weight vector. And again, we can do this over and over again. This data is fake. It's easy to generate. You can generate lots of it. And you can train actually smallish models, as we're going to see later on, to do pretty well on this objective. So what happens when you do this? And so the first thing that we're going to look at here is just the quality of the predictions that the model is making. So notice here that when we're actually oh, the axis labels got chopped off, but we'll explain these in a minute. When we are sampling from the model, right, at no point are we asking it to explicitly exhibit an inferred parameter vector. We're just asking it to predict our y's from our x's. And for all of the plots that I'm going to show now, we're going to look at 8-dimensional problems. So unsurprisingly, right, with fewer than 8 examples in the input, the model can't possibly know exactly what noiseless linear function it's trying to learn. And so you get some high error rate that declines gradually over time. So this is just the sort of squared error for the predictions made by the model. All of the other lines that I'm going to show right now are not agreement with ground truth, but agreement with other prediction algorithms that we can fit to these data sets that we're handing to our transformer model to do ICL, right? So we might, oh yeah, question. Sorry? Yeah. Just one epoch, yeah. So it just sees, you know, XY, XY, XY in sequence without repetition. Yeah. Other questions about the setup? Okay, good. So what we're going to ask now is, you know, not just what's the fit of this model to the sort of ground truth labeling function, but to other learning algorithms that we might train on the same data. We might hypothesize, and in fact, people in the NLP community have hypothesized that the right way to think about ICL is that it's doing something like nearest neighbors, so we can fit some nearest neighbors models. And those don't actually seem to do a very good job at all of describing the kinds of predictions that this transformer makes. You can do SGD. And you know, various versions of SGD and gradient descent where you look at all the examples in a batch or you look at them one at a time. All of these things early on seem to agree relatively well with the model's predictions and you know, sort of diverge around that critical example and then start to fit again better later on. You can ask about, you know, more sort of old school, I guess not old school, but standard regression algorithms. Here we're looking at regularized you know, ridge regression here. This is a noiseless problem, so you shouldn't need this in principle. Nevertheless, this gives us a really pretty good fit to our data, but maybe unsurprisingly, right, if you just do ordinary least squares, taking the min-norm solution in this less than 8 regime, this is almost a perfect fit to the predictions that these models are making. So they really do seem to be behaving, now without saying about the sort of anything about the computations that support them, or support that, but behaving like these OLS type models. And this, you know, maybe should not surprise us, right? If this is really our data generation process, we know that the min-Bayes risk predictions are going to come from a weight vector that looks like this. And so if we could really drive this loss function all the way down to 0, in some sense what we would have to do would be to make predictions that look like this in this noiseless regime. And you know, we can sort of stress test this a little bit by changing the data generation process such that the min-risk predictor looks a little bit different. We can make it, for example, we can add some noise to our y's so that now the right thing is to behave as though you're regularized a little bit, right? And we know in particular for particular distribution of weight vectors, particular distribution of noise being added to these y's, that there's a nice closed form for the ground truth predictor here in terms of these two things. And so, you know, you can do something that looks like ridge regression with a parameter that's determined by these two noises. And when you do this and you ask these questions about what's the sort of best fit to the model, you again see exactly the pattern that you want to see here, right? That when there's no noise at all, the fit to OLS is better than everything else. As you start to add noise either to the data generation process, or sorry, either to your X's either to your W's or to your Y's given W's, you see this nice pattern where the predictor that best fits the predictions that you actually get out of this transformer are exactly the ones that you would expect if you were just trying to minimize risk. You know, so this is just saying that this sort of finding before is robust, that basically these models, at least at the scale that we're training them, do actually give you exactly the predictor that you want for these kinds of linear regression problems. And this agrees with that Garg et al. Paper that I was talking about before that does similar kinds of experiments also in the presence of you know, sort of sparse X's, sparse W's, things like that. A more interesting question that we can ask here is whether this always happens, or whether in the sort of presence of stronger computational constraints than we have assumed up to this point, models are still able to sort of perfectly fit these distributions, or whether they do something different. And the cool thing that happens here is that you actually get different fits to different algorithms as a function of model size. So as we make, you know, for the sort of very shallowest models, if we only give them one layer, they are not perfectly described, but best described as doing something that looks like a single step of, I think I've covered this up on the legend, but of actually batch gradient descent on the input. As you make these models bigger, they look a little bit less like they're doing gradient descent and a little bit more like they're doing properly squares. And you know, as you make them big enough, like we've been doing before, you converge to that OLS solution. You can also look at this as a function of the hidden size of the model, the size of these embedding vectors that we're passing up. And here you see less clear, but also a similar kind of trend, where for very, very, very small hidden sizes, you have a slightly better fit, but not a great fit from these SGD type predictors, and at bigger sizes, you have a better fit from the right ones. And so we can think of there being a couple kind of phases or regimes in model parameter space, in model architecture space that describe the kinds of algorithmic solutions that these models find to this regression problem. And we're going to look later on specifically at this sort of SGD regime and try to figure out better what's going on there. The last question that we are going to ask about these trained models before we do that is just whether we can figure out anything at all about what's going on under the hood. So far, all of the characterization of real models that we've done has been sort of extensional, right, in terms of their functional form and not in terms of their internal computations. But it's reasonable to ask, given that we have these sort of constructions lying around for what intermediate quantities you might need to compute in order to solve these problems, whether we can see any evidence that trained models are actually computing the relevant intermediate quantities. And so to do this, we're going to do what's called, I guess now in the ML literature, a probing experiment. We're going to take our original trained model. We're going to freeze its parameters. And we're going to fit some teeny little model, either just like a single linear readout or a tiny little multilayer perceptron. And we're going to train this probe model to try to predict what the real optimal W hat was for the problem that's being presented in the input from the internal states of the transformer model. So basically, can I just look at one of these hidden states and recover with some predictor that's not powerful enough to like solve the linear regression problem on its own, the predictor that we think the model is using to actually make predictions. And so you can do this for different kinds of intermediate quantities that you might want to look for here. The natural one is just this weight vector, right? We said before, we're never actually showing the model any weight vectors. We're never asking it to generate a weight vector. But if you try to probe for this weight vector in its intermediate states, you find that you can do that, and you can actually do it pretty well with linear readout right near the end of the network. Which I think is exactly what we would have expected from the little construction that we gave before. As some sanity checks here, right, you can try doing this on a model that is trained to perform some task that requires you to look at all of the inputs and outputs, but is not linear regression. And for those, what we're calling control tasks, no matter where you look in the network, you don't acquire the ability to recover W as accurately as we were here. So some evidence that, in the course of making the predictions that we were looking at before, our weight vector actually gets encoded by the models that are making these predictions, which is a cool thing to find. We can ask about other relevant intermediate quantities, right, just like the product of our X matrix and our Y matrix. And if we do this, the story is a little muddier. It's definitely not linearly encoded. Maybe it's non-linearly encoded, and the evidence that it's non-linearly encoded is the sort of gap between this control task and the real task, which is not as big as we were looking at here. But to the extent that there's anything going on, it's going on much earlier in the network, that the model sort of computes this around layer 7 or layer 8, and then hangs on to it. And again, this is a little bit more speculative. I wouldn't take this as like dispositive of models computing this quantity, but it is what we would expect if it were implementing one of these algorithms that we looked at before, because this is a sort of first step that you need to do in order to compute the W later on. Good. So to come back to all of these questions that we were sort of asking at the beginning of this talk, right, what is in-context learning? And the sort of main hypotheses that we want to discriminate here are whether it's task identification or quote unquote real learning. And in the context of a very, very, very simple real learning problem, we've shown that it's possible, at least in principle, that models are really doing it, that you can get smallish transformers to implement real learning algorithms. And we've presented both sort of behavioral evidence and at least preliminary representational evidence that this is actually what's being implemented by these models, at least at the scale that we're looking at. So in, I guess, the little bit of time that I have left before I switch over to questions, one thing that's been really fun, this was obviously a question that was like very much on people's minds, I guess a year ago, last summer when we started doing this project. And there's been a ton of work that's come out in this space, both kind of concurrently with what we were doing here and since this paper came out. So, some natural questions that you might have at the end of everything that I've been showing here is whether these constructions we've given are actually the right ones, or whether, especially given that we were getting pretty good results from like 2-layer transformers, 4-layer transformers, whether we can do these things more efficiently, whether we can say anything, sort of theoretically about the conditions under which we're actually going to recover the real learning solution, and how this relates to data distributions both in these kinds of synthetic models and in real models. And what's nice is that we're starting to get answers actually to all of these questions. So shortly after we did this, there was a paper actually also from another group at Google that I guess had not been talking to our Google collaborators, showing a very similar thing, showing that you could get standard transformers to implement, in this case, fitting these linear regression problems via a single step of gradient descent. And they do it in a very different way. They use the attention mechanism actually to compute all of the dot products that you need to compute. And this allows them to do it in a single layer with a single attention head. And so if you think back to those kind of experimental results we had before, right, showing that in the single layer regime, we're looking more like a one-step of gradient descent model than anything else. Here is now some evidence, or here is an example of a way in which you can solve this problem by parameterizing a transformer that would generate exactly that behavior for you. There's one kind of important caveat here, which is that this is not actually using the kind of real models that people train in practice, but something with a slightly simpler and slightly less expressive attention mechanism, and this might account for the little gap that we were seeing between our SGD predictors and the real model behavior. Even cooler, very recently, some folks at Berkeley, I think Spencer is now at UC Davis, but showed that not only can you do this, but you are, under certain conditions, guaranteed to converge to exactly this linear self-attention one-step of gradient descent solution. So we can say now a little bit more precisely the conditions under which in-context learning really is real learning, and you can actually guarantee this up front using this linear self-attention model. Finally, all of these interesting questions about data sets. So one, and I think this is a very recent paper, but cool thing that came out, right? You can imagine that if you only ever trained your model at training time on outputs from a single weight vector, the right thing to do, kind of no matter what, is to not do any in-context learning. Just memorize that weight vector and use that weight vector to predict whatever Ys you're going to see at test time. And so there's a sort of question of whether, like, how much diversity in that training set you really need to see before you switch over to being a real learner as opposed to something that's memorized a fixed family of weight vectors. And so now some empirical evidence that you do get exactly that kind of, again, phase transition as a function of the diversity of the data set, that for small Ws, or a small number of Ws, you memorize all the Ws. For a sufficiently large number, even finite of Ws that you get to see over and over again during training time, eventually you learn to do in-context learning. Instead, I think this is especially interesting because it sort of goes against that min-Bayes risk story that I was talking about before. When you're in the regime of having a finite number of Ws that you've ever seen at training time, probably the right thing to do is eventually, or, at least sort of in a Bayesian sense, is to just memorize that large finite set of Ws. Models don't do that, and at some point they learn the solution that generalizes instead. And finally, we can start to ask these kinds of questions about real models. Thinking back to the very beginning of the talk, right, we had this kind of back and forth between, is this just task identification? Is this real learning? And now some empirical evidence that, in fact, it's a mixture of both, and that you can, by changing the label distribution or the kinds of instructions that you provide up front, actually induce models to behave more like task identifiers or more like in-context learners, again, just by sort of manipulating the inputs. Finally, oh man, everything moved around on the slide. But one thing that we've started to look at that's a sort of next direction that I'm super excited about is generalizing to more interesting kinds of prediction problems, right? So we can ask now not just to produce a single categorical label for these things, but more structured kinds of outputs that maybe start to look a little bit more like the kind of real machine translation examples and other text generation examples that we saw at the beginning of this talk. what we're looking at specifically is in-context learning of finite automata and other sort of formal languages. And here it turns out that at least empirically, right, these models are also very, very good at doing this in context. You can get close to perfect accuracy. And interestingly, this seems to be a task that separates these transformers, this sort of current architecture, from a lot of the other work that has been done in recent years, trying to propose new kinds of models that are easier to train, have lower computational budgets, things like that. And so ICL, right, this in-context learning thing seems not only to be a sort of surprising property of these models, but not something that you necessarily get for free at scale in any sufficiently large neural sequence predictor. There is something special about transformers, and so the question is, what is that thing? And ultimately, if we can answer that question, we will hopefully know what we need to do to figure out what the next generation of model architectures looks like. With that, I will wrap up. As always, most of the credit goes to Ekin, and the rest equally distributed among our collaborators. This was a super fun collaboration, and happy to answer any questions.